Aspergillus fumigatus is a pathogenic fungus commonly found in all parts of the world, particularly old buildings and soil. Most people inhale Aspergillus fumigatus without issue, but among the immunocompromised, the spores can develop into a condition known as aspergillosis, with up to 90% fatality rates. As of today, there exists no preventative system to identify Aspergillus fumigatus spores in the air.
Breaking news: The Sentinel, a system developed at the University of Manchester to collect, detect and identify the Aspergillus fumigatus spore, was recalled today due to being unable to achieve the resolving power to image the fungus. A spokesperson from the university has indicated that work is underway to address this issue. Back to you.
This project aims to demonstrate a proof-of-concept optical system utilizing computational microscopy in reflectance mode to achieve the resolving power needed to image Aspergillus fumigatus spores. Fourier ptychography was identified as a computational microscopy technique capable of combining multiple low-resolution images into a single high-resolution reconstruction. To do this, the system must be able to capture images illuminated from known angles of illumination across a variety of angles with a consistent area of illumination. The system was designed to translate and collimate light from the LED array onto the sample, which is then reflected through the lenses into the camera. This design was adapted from a paper, further broken down into 2 light paths, and verified using Oslo simulations. Initial designs included a method of varying the focal plane of the camera, but this had to be descoped. Using this optical arrangement, 6-micron features on the sample could be resolved. Based on contrast analysis, this is an improvement of 21.7% over the Sentinel imaging system. Image acquisition tasks relate to the control of electronic components in the prototype system. This involves implementing a user interface which controls the illumination sequence and camera exposure. For the camera control, a variety of exposure modes were evaluated for this purpose, with the optimal for this project being identified as the night mode, which minimized saturation in the image. In parallel with the design and implementation of the optical system, a Fourier ptychography algorithm was developed alongside a simulated dataset. To assess the effects of changing key parameters, the reconstruction of the simulated dataset was measured using SSIM, an image similarity measure. From these results, the ideal parameters were identified and implemented into the final algorithm. The following noteworthy achievements of the project include: successful capture of images resolving 6-micron features on a sample in reflectance mode using on-axis illumination. Contrast analysis showed an improvement of 21.7% over the Sentinel system's imaging capabilities. Production of a GUI for the embedded system with consideration to future use cases. Creation of a Fourier ptychography algorithm and simulation of a dataset to test effects of varying parameters. The following challenges were encountered. The illumination path of the optical system was not able to provide the wide angles of illumination needed for Fourier ptychography. The focal plane variation was not able to be implemented, so that requirement of the design was descoped. The planned manual calibration of the camera could not be implemented, as this process was time-consuming and needed to be repeated for every new experimental setup. The Fourier ptychography algorithm was implemented in its most basic form, which left it susceptible to aberrations in the optical system. The team was able to identify the conflicting constraints which hindered the success of the project. This insight was used to identify avenues for future work. Aspheric lenses could reduce aberrations in the optical system. The illumination system could be furthered by the inclusion of dark field illumination. Alternative strategies for image acquisition were identified, such as a system capable of detecting a change on the sample before acquiring data, or utilizing multiplexing in the Fourier ptychography algorithm to capture images illuminated from multiple angles simultaneously. The Fourier ptychography algorithm could be improved by aberration correction or the use of neural networks for the reconstruction process. Focal plane variation implementation could involve utilizing a piezoelectric motor, although this will not fit with the low-cost limitation.